Okay, here we go with our guided notes for 3.5. We're going to start with our definition of rational functions. If p of x and q of x are both polynomial functions, then my function f of x equals p of x over q of x is a rational function so long as that denominator q of x is not 0. We know that when our denominator is 0, our function is undefined. So our domain, therefore, is restricted to all real numbers that do not cause the denominator to be 0. What this definition tells us, in a nutshell, is that a rational function is going to have a variable in the denominator. That's what visually cues us in, if we have an equation, that we have a rational function, because that variable shows up in the denominator. Now, hopefully you have watched the video for the examples of graphs of rational functions, so you have looked at some examples of what rational functions can look like, and we've talked about the different rational functions. A rational function will have values at which the graph is undefined. That means that our domain is not all real numbers. These values where the graph is undefined are going to show up as either asymptotes, vertical asymptotes. Oh, I'm sorry. I should have read ahead. I didn't read ahead. Holes. They're going to show up as holes if the function is not in lowest terms. That's why my blank was so small. So you're going to have a hole in the graph if the function is not in lowest terms, or as vertical asymptotes where the function is in lowest terms. Asymptotes is spelled A-S-Y-M-P-T-O-T-E-S. Vertical asymptotes. And here you go. Definition of an asymptote. An asymptote occurs at a value the function approaches but never reaches. An asymptote is a value that the function is going to approach but never ever get to. All right, holes and vertical asymptotes. And we're going to refer to vertical asymptotes notationally with a VA. Horizontal asymptotes HA, slant asymptote will be SA, like we did on our examples page. Holes or vertical asymptotes are determined by the domain, the denominator of the function. The domain, the values we exclude from the domain, come from the denominator. That tells us what to exclude. You can have more than one vertical asymptote or hole in the graph. Now, like we saw back on that example sheet that we just worked through in the other video, like we saw in those examples of rational functions, if you have a value for which the function is not in lowest terms, so we're going to kick that out of the domain, but it doesn't stay as part of the function. Holes, that becomes a hole. A hole occurs for any value from the denominator that factors out. If it factors out because the function was not in lowest terms, it gives us a hole in our graph. Now look back on that examples page, right here, example number 6. We had a hole in the graph. That hole occurred because when we factored our function, we factored our numerator, we factored our denominator, we saw that there was a factor that would cancel out. This x plus 1, if I set that equal to 0, I get x equals -1. That is a value that gives me a hole in the graph, not a vertical asymptote, because the function is not in lowest terms here. Vertical asymptotes, however, occur for any values from the denominator that remain. So if the function is in lowest terms, nothing cancels out. Those values give us vertical asymptotes. Each vertical asymptote is like a brick wall. It is never crossed. Now, we already did this in the other video. We found the vertical asymptotes and holes of the examples of the rational functions. Function 7 had a hole in the graph because it had that common factor in the numerator and denominator, x plus 2. That fact, I had to kick that out of the domain. It is not included in the domain, but since it factors out because the function is not in lowest terms, that value, x plus 2, when I set it equal to 0, gives us -2, and that gives us a hole in our graph, not a vertical asymptote. All right, horizontal or slant asymptotes. Another word for a slant asymptote is an oblique asymptote, and you'll see it referred to that in some of the paperwork. Some books will refer to those as oblique asymptotes instead of slant asymptotes. These asymptotes apply primarily to the end behavior. So I can cross a slant or oblique asymptote. There will never be more than one. I will only have one of these, one or the other. And I figure out what I have, whether it's slant or oblique, and where it occurs by the degree of the numerator compared to the degree of the denominator. Compare the degree of the numerator to the degree of the denominator. There are 3 different ways these degrees can compare. So I have 3 different cases. Now remember that we are sticking with linear asymptotes in this course. If you had different situations, you could have asymptotes that are not linear. We're not worrying about those for this class. If the degree of the numerator is less than the degree of the denominator, then my horizontal asymptote is equal to the x-axis. So the equation of that asymptote is y equals 0. For example, if I have the function f of x equals 2x plus 3 over 5x squared minus 5, well, the degree of my numerator is 1, the degree of my denominator is 2. So the degree of the numerator is less than the degree of the denominator. My horizontal asymptote is at y equals 0, the x-axis. If I had the function, for example, g of x equals 7 over x to the 5th plus 3, well, the degree of my numerator is 0 because I would have, x to the 0 is just 1. So I don't even have an x up there. The degree of my denominator is 5. So the degree of the numerator is absolutely less than the degree of the denominator, which means I have a horizontal asymptote at the x-axis, y equals 0. The second situation that can occur when I'm comparing the degree of the numerator to the degree of the denominator is that those 2 degrees are equal. When that happens, I have a horizontal asymptote at the ratio of the leading coefficients. I have a horizontal asymptote, and it occurs at the ratio of the leading coefficients. So let's just adjust that f of x and g of x up here to make it a situation where our degrees are equal in the numerator and the denominator. So for f of x, I'm going to rewrite that as 2x squared this time plus 3 over 5x squared minus 5. And for g of x, I'm going to rewrite that as 7x to the 5th over x to the 5th plus 3. Notice that for both of these functions, now the degrees are equal to each other. Degree of the numerator is 2, degree of the denominator is 2. For g of x, degree of the numerator is 5, degree of the denominator is 5. When that happens, I know I have a horizontal asymptote at the ratio of the leading coefficients. Well, leading coefficients right there. So my equation for my horizontal asymptote is y equals 2/5. For g of x, the degrees are equal. So I have a horizontal asymptote at y equals, well, 7 over 1 is just 7. So that horizontal asymptote has been shifted up to a positive 7 on the graph. The third case, if the degree of the numerator is not less than or equal to the degree of the denominator, it must be greater than the degree of the denominator. Now we are going to limit how much bigger. Remember I said that you can have different types of asymptotes. Well, we're going to say the degree of the numerator is 1 more than the degree of the denominator. It's greater than, but it's just greater than by 1. If it were greater than by 2, we'd have a parabolic asymptote, etc., etc. We're not going to go there. When that happens, we have a slant asymptote. That slant asymptote is equal to the quotient. So I have to do my division. If it's 1 more than, the degree of the numerator is 1 more than the degree of the denominator, then I have a slant asymptote. Let's go back to our equations up here and look at what, oh no, don't do that. Let's do something where we can find a slant asymptote. Let me see if I have a good, oh, yep, here we go. Here's a good example. So we're going to do f of x is equal to 2x squared plus 3x minus 5 over x plus 2. When I compare the degree of the numerator to the degree of the denominator, I see that the degree of the numerator is 1 more. So I know I'm going to have a slant asymptote. Let's think about vertical asymptotes or holes first. Let me make sure I haven't jumped ahead, and because this is my first time through this set of notes. No, I have not. We're good. Okay, if I think about vertical asymptotes or holes, let's just start with our domain. Our domain of our function, what do we need to leave out? Well, we need to leave out anything that would cause me to have a 0 in the denominator. If I set this x plus 2 equals to 0, I find out that I have to exclude a -2 from my domain. And because my function's in lowest terms, this is not going to factor. That means that that value excluded from my domain gives me a vertical asymptote, not a hole. There are no holes for this function. My equation for my vertical asymptote is going to be x equals -2. X equals -2. So let's sketch a really quick graph. Over here. So if x equals -2, then at -2 I have a vertical asymptote. Don't have any holes in the graph, but at -2 I have a vertical asymptote. We said we compared the degree of the numerator to the degree of the denominator. So when I figure out whether I have a horizontal or a slant asymptote, I know it's going to be a slant asymptote because that degree of the numerator is 1 more than the degree of the denominator. To figure out what that slant asymptote is, I have to do my division. Let's set it up. Let's say x plus 2 divided into 2x squared plus 3x minus 5. All right, we've set up our long division problem. We ask ourselves, how many times does x go into 2x squared? What times x gives me 2x squared? Well, that's going to be a 2x. Then I multiply. 2x times x is 2x squared. 2x times 2 is a positive 4x. And then I subtract. And when I subtract everything out, it changes the sign. So this becomes a -2x squared that adds to 0. This becomes a -4x that gives me a minus x. And I bring down my -5. All right, so what times x gives me -x? Well, -1. Now that I filled in my quotient line, I multiply. -1 times x is -x. -1 times 2 is -2. And I subtract. When I distribute this negative inside, that becomes a positive x that adds to 0. When I distribute this negative inside, that becomes a positive 2. -5 and positive 2 is -3. But that's my remainder. My remainder doesn't affect the equation of the slant asymptote. My equation of my slant asymptote is right here. So my slant asymptote is y equals 2x minus 1. How do I graph y equals 2x minus 1? Well, to graph y equals 2x minus 1, the easiest way is to start with a y-intercept. In this case, that is -1. So right there, -1 is my y-intercept. And then I'm going to apply the slope. My slope is a positive 2. So from this point, I'm going to go up 2 and over 1 to get to the next point. Up 2 over 1, up 2 over 1. And I get this line with a positive slope. That is my slant asymptote. This note tells me to go back and go ahead and find the equations of the horizontal and slant asymptotes of those examples. We already did that. Let's finish off this graph. Now, typically, what you're going to find is that when we have a vertical asymptote and a slant asymptote, we divided our graph into 4 sections. Those sections are not equal sections, but we have divided our graph into 4 sections. And if you try to visualize this, I've got this big wide section here on the right and this big wide section here on the left where my function can be turned by those asymptotes. And then I've got these skinny sections, this section in here and this section down here. Now, most of the rational functions you're going to see are going to exist in that way. They'll either be in the two wide sections or the two skinny sections. Now, vertical asymptote, because this is a function, it can't exist here and there because then it would fail our vertical line test. So it's going to be either these two wide sections or these two skinny sections. And we need to do a point to see where it falls. When I try to go to figure that out, a good point to check would be maybe what happens where x is 0? Where does my function fall? If x equals 0, what is y? So I'm going to go to my function and I'm going to say, okay, let's find f of 0 and see what happens. Well, 2 times 0 plus 3 times 0 minus 5 over 0 plus 2. Everything goes away except negative 5 over 2. Well, where x is 0, y is a negative 5 halves. Well, what is negative 5 halves? Negative 5 halves is the same thing as negative 2.5. We said this was negative 1, so negative 2.5 is going to be right about there. And that tells us where this piece of the function is. It's down here, not in that skinny section. And remember what I said, if it's in this wide section on the right, it's probably in the wide section on the left. How would I know for sure? Well, I could check another x value. This vertical asymptote goes through negative 2. Let's do negative 3 as an x value. So let's go back to our function, f of x, and find f of negative 3. We've got 2 times negative 3 squared plus 3 times negative 3 minus 5 all over negative 3 plus 2. Well, negative 3 plus 2 is just negative 1, so that's easy. That's lovely. My numerator becomes 2 times 9 minus 9 minus 5, and my denominator is negative 1. My numerator is going to be 18 minus 14, which is 4, but 4 divided by negative 1 is negative 4. So we find the point where x is negative 3, y is negative 4. That's a point on my graph. Where x is negative 3, y is negative 4. Now this is a little wishy-washy. It's kind of hard to, on my hand sketch graph, it's hard to see exactly where that would be. So I'm just going to be confident with you that we are correct. Remember on my math lab, you get to use my math lab for all of the homework, and you're going to know for sure because you're going to plug in some points and it's going to tell you where the function falls. Symmetry of functions. A symmetry of function reminder here. Symmetry of functions, checking symmetry, saves you time in making an accurate graph. If you know your function has a type of symmetry, then you know where the function falls and you don't have to check as many points. We already did this. We already found the expected symmetry for the examples of the rational functions in our other video. I encourage you to go back again and rewatch that video. All right. For each graph below, we are given graphs. For each graph below, we're going to find the domain, the equations of the asymptotes, symmetry, and we're going to describe what the function is doing as x gets large and as x approaches vertical asymptotes. What is the function doing as x gets large and as x approaches the vertical asymptotes? Okay, so for this first graph, domain. Well, I can see that my function has a vertical asymptote here and a vertical asymptote here. And I can be fairly confident that those fall at positive and negative 3. So my domain excludes only those values. My domain is all values of x such that x is not negative 3 or positive 3. That's number 1. That's the domain of my function. I see that those are asymptotes. I have those two vertical asymptotes, and then it looks like I have this horizontal asymptote right here at the x-axis. So number 2 tells me to give the equations of all asymptotes. I have two vertical asymptotes. My equations for vertical asymptotes start as x equals. Then I have a horizontal asymptote at the y-axis, at the x-axis, so that equation is y equals 0. Symmetry. When I look at my function, now it didn't give me the equation, I can't graph this function, but I can look at the function and determine symmetry. Do I have an even function or an odd function? If I have an odd function, it would be a twist. Don't have a twist. If I have an even function, I can fold it on the y-axis. If I fold this in half, do the sides match? Yes, they do. Because if I fold it on the y-axis, these two outside ends are going to match up, lay on top of each other, and this middle is going to match up and lay on top of itself. So this function is an even function, and it has y-axis symmetry. My fourth question is kind of a big question. It asks me to describe the behavior as x approaches infinity and as x approaches those vertical asymptotes. So we've got two statements for this, positive and negative infinity. And then we've got two different vertical asymptotes. So we've got to come at those vertical asymptotes from both directions. Let's start by talking about what happens as x gets large. So as x approaches positive infinity, so as x goes this way, I can see that my graph is getting closer and closer to that horizontal asymptote at 0. So as x goes to positive infinity, y approaches 0. It approaches that horizontal asymptote. What about as we go to negative infinity? As x approaches negative infinity, well, on this other end of my graph, as I go this way, I'm getting again closer and closer to the horizontal asymptote, which is 0. So y approaches 0. That's my, as x gets large. Now let's do what happens as I approach the vertical asymptote, x equals -3. Well, as x approaches -3, but I'm interested in it moving from the positive direction. So as I move toward this vertical asymptote from the positive direction, so as I'm moving on this piece of the function, I see that my function value is plunging down and y is approaching -infinity. However, as x approaches that asymptote at -3 from a negative direction, as I come in toward this asymptote from a negative direction toward the asymptote, y is going up. Here, y is approaching positive infinity. And then I have one more vertical asymptote to consider. I have another vertical asymptote at +3. So I have two more of those statements, and my other two statements are happening right here as x moves toward this vertical asymptote. So as x approaches +3, this vertical asymptote, from a positive direction, what is y doing? Well, y is going up, so y is going to positive infinity. And as x approaches that value 3 from the negative direction, well, right here, that's this piece of the function, and y is going to -infinity. All right, let's work through these four for this next graph. Again, I have two vertical asymptotes and one horizontal asymptote. First statement, what's my domain? Well, my domain excludes the values for those vertical asymptotes. Number 2 asks me to give the equations for my vertical and horizontal asymptotes. I have two vertical asymptotes, x equals -1, x equals +1. I have a horizontal asymptote. This horizontal asymptote is also at the x-axis. That equation is y equals 0. Symmetry. When I look at my function and consider symmetry, I see that I've got one end up, one end down, and a twist in the middle. That is an odd function with origin symmetry. It is symmetric about the origin. All right. So let's do our statements about what y is doing as x gets large. So number 4, as x approaches infinity, so as x gets large this way, y is getting closer to that horizontal asymptote. Y is approaching 0. As x goes to negative infinity, y is still approaching 0, just from the other direction. So that statement is always going to be the case, because the purpose of a horizontal or slant asymptote is to tell me what's going on as x gets large, what happens at the ends of the function. The next set of statements are going to be for what happens as I approach that vertical asymptote -1. As x approaches -1 from a positive direction, and as x approaches -1 from a negative direction. Well, as x moves toward -1 from a positive direction, this function, as I'm moving toward -1, my function is going to negative infinity. Y approaches negative infinity. As x approaches -1 from a negative direction, though, so from negative infinity, I'm moving toward this first vertical asymptote, it's going up. Y is approaching positive infinity. Then we have one more vertical asymptote to consider. And we need to think about what x is doing as it approaches that asymptote from a positive direction, and what x is doing as it approaches that asymptote from a negative direction. What is y doing? What's my function behavior look like? Well, as I come in toward this asymptote from a positive direction, my y value is dropping. Y is going to negative infinity. And as I come into that vertical asymptote from a negative direction, y is going up. So y is going to positive infinity. Remember that you can absolutely pause this video, rewind it, so that you can go back through things that you are struggling with. All right, let's do a little bit of graphing practice. Graphing some rational functions. Okay, I'm going to start by looking at my function to see if it is factorable. And then I'm going to stop and I'm going to answer some of these questions before I do anything else. So when I look at my function, I see that my numerator is x plus 5, nothing to do there. But my denominator is difference of squares. That absolutely is factorable. So that factors out, difference of squares is going to factor out to give me a conjugate pair, x plus 5, x minus 5, which means my function is not in lowest terms. Now, when I see that my function is not in lowest terms, that is important to me because I need to know that that means I will have a hole in the graph. Now, stop and consider domain before we go any further. Any values that would give me zeros in the denominator, whether it's in lowest terms or not, have to be excluded from my domain. So I'm immediately going to say, okay, my domain, all values x, except -5, +5. Those are the values I need to kick out of my domain. One of those values is going to give me a hole, and the other value is going to give me a vertical asymptote. But the next question, do I have symmetry? Can I make it easier on myself graphing if I consider symmetry? So let's think about that. Let's think about if I plug in a negative x, what happens? Well, if I plug in a negative x, oh, see, my denominator doesn't change. It stays just what it is. But my numerator, just one term changes sign. Yeah, that's not going to help me. There is no predictable symmetry. Not predictable. My numerator has one term that changes sign. That denominator doesn't do anything. It just stays x squared minus 25. But my numerator, one term changes, one term doesn't. Not predictable symmetry. That does not help. Okay, to figure out asymptotes and holes, I need to go ahead and think about what happens with my function getting it into lowest terms. This is my factor that cancels out. X plus 5 over X plus 5 is just 1. So in lowest terms, my function looks like this in lowest terms. This factor canceled out. That value gives me a hole in the graph. This factor stays put. That value gives me a vertical asymptote. If I take this expression x minus 5 and set it equal to 0, what do I get? Well, I get x equals positive 5. That is the location of my vertical asymptote. Let's sketch that in. A vertical asymptote at x equals positive 5. Then I have to deal with what factored out. Well, this expression factors out, x plus 5. If I set that equal to 0, I discover that I have a hole in the graph at negative 5. Ooh, that's going to be something I need to remember. I'm going to have a hole at negative 5 when I sketch my graph. So I'm going to kind of mark that with a little H over there to remind myself to do that. Okay, next question. Horizontal or slant asymptote. To answer that question, I compare the degree of the numerator to the degree of the denominator. In this case, the degree of the numerator is 1, denominator is 2, or if I look in lowest terms, the degree of the numerator is 0 and the degree of the denominator is 1. Either way, the degree of the numerator is less than the degree of the denominator, which means I have a horizontal asymptote, and that horizontal asymptote is the x-axis. When the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at the x-axis. So I can sketch that in. The equation of the x-axis is y equals 0. I see from my asymptotes why I do not have predictable symmetry. I've taken my function and I've shifted it away from the origin. So there's no way it's going to have origin symmetry. There's no way it's going to have y-axis symmetry because I have shifted it over to the right. Okay, y-intercept and x-intercept. You know how to find this. This helps me start figuring out where my function is going to fall. The y-intercept happens where x is 0. Where x is 0. Well, if I find g of 0, that gives me 0 plus 5 over 0 squared minus 25. That is 5 over negative 25, which is a negative 1/5. 0, negative 1/5. So my y-intercept is just below the x-axis. You know what? Looks like this piece of my function is going to be right here because these asymptotes turn my function. So I expect this piece to be right here. X-intercept happens where where y equals 0. Where y equals 0. So let's find that x-intercept. Ooh, am I going to have an x-intercept? Probably not. Why do I say probably not? Well, my x-axis is a horizontal asymptote. So I don't expect I'm going to have an x-intercept. But let's check it out. Let's set y, or g of x, equal to 0. And that gives me x plus 5 over x squared minus 25. To do this, every time I multiply both sides by the denominator because that allows me to cancel that denominator out over here. 0 times anything is 0, and it gives me 0 is equal to the numerator. Well, 0 equals x plus 5. I subtract that 5, I get negative 5 equals x. And you know what? That is outside my domain. That value is excluded from the domain, so there is no x-intercept. That's what we expected. So we know our function has to go through this point, and I've got a hole right here. So I can start by saying, you know what? I got a hole here. It's going to hit this point, and it's going to come in closer, and it's going to turn, and it's going to go down there. That's this left-hand piece of my function. Now, if I go back and look at my examples of rational functions, and I try to find one that looks kind of like this, you know what? That looks a lot like this number 1. 1 over x minus 5 is a lot like 1 over x. It's just that I don't have this minus 5. Well, 1 over x had a vertical asymptote at 0, down and then up. 1 over x minus 5 has a vertical asymptote at 5, down and then up. That looks like a horizontal shift to me. Let's check. Let's check an additional value for x, something over here on this side of my vertical asymptote. My vertical asymptote is at 5, so let's check x equals 6 and see what happens. If I take 6 and I plug it in for x, g of 6, that's 6 plus 5 over 6 squared minus 25. Well, 6 plus 5 is 11. 6 squared is 36, minus 25 is 11. 36 minus 25 is 11. That's just 1. So that gives me the point 6, 1 on my graph, where x is 6, y is 1. Look at that. That's exactly where I thought this piece of my function would be. Ta-da! That's supposed to be a curve. I'm sorry, it kind of looked like an angle. It's supposed to be a nice curve. So that's graphing one of our rational functions. Looking through to see how many more we have to graph. This video is getting a little long. We're going to graph one more, and then I'm going to post the key, I think, for the next page. But we're going to look at that last page together where we have multiple choice. All right, so let's walk through this function. If I look at my function, f of x, it's not factorable. It's already in lowest terms. Since it's in lowest terms, I know that I won't have any holes. Nothing's going to factor out. To find anything excluded from the domain, I look at the denominator. So I take 2x plus 5, set that equal to 0, and figure out what would make that happen. So that gives me 2x equals negative 5, divide by 2, and I get x equals negative 5 halves. That is the value I need to kick out of my domain for this function. So I'm going to say all values of x except negative 5 halves. Now remember that negative 5 halves is the same thing as negative 2.5. Because my function's in lowest terms, I don't have any holes. This is a vertical asymptote. Vertical asymptote at negative 2.5. Negative 5 halves is negative 2.5. So let's go ahead and put that on our graph. Negative 2.5 is going to be right here. There's my vertical asymptote. Symmetry. Let's check out symmetry to see if our function has any symmetry. Let's think about f of negative x. If I plug in f of negative x, that gives me negative 4 times negative x is a positive 4x plus 5. And I've got trouble right there. I've already got trouble. Since one term changed sign in my numerator and the other term didn't, I don't have any symmetry. I can stop right there. It's not predictable. So now let's think about horizontal versus slant asymptote. To figure that out, I compare the degree of the numerator compared to the degree of the denominator. And when I look at that, I see they're both first degree. So it's equal. When those two degrees are equal to each other, I have a horizontal asymptote at the ratio of the leading coefficients. Well, my leading coefficients, negative 4 over 2. Negative 4 divided by 2 is negative 2. So y equals negative 2. That's my horizontal asymptote. Y equals negative 2. So I can see why I didn't have symmetry. I took my function, I shifted it to the left and down. So yeah, it's not centered on the origin, it's not centered on the y-axis, no predictable symmetry. All right, y-intercept and x-intercept. Y-intercept happens where x is 0. If I take x is 0, f of 0 equals, well, that's 0, so that would be 5. That's 0 over 5 is 1. So I have a y-intercept at 0, 1. Looks like this piece of my function is going to be up here, above the horizontal asymptote, to the right of the vertical asymptote. just like it's above and to the right on my last function. So I kind of expect that maybe the other piece is going to be over here. But let's finish this and see what else we've got. X-intercept. We can have an x-intercept here because our x-axis is not our horizontal asymptote. So this is a good chance to look and see what happens when y equals 0. So y equals 0. I set my function equal to 0. I'm going to need to multiply both sides by 2x plus 5. But anything times 0 is 0. So every time this remains 0, and I have 0 is equal to the numerator, and I have to solve. So I'm going to subtract 5. I get negative 5 equals negative 4x, and then I divide by that negative 4, and I get x equals a positive 5/4. Well, 5/4 is 1 1/4. So where x is 5/4, y is 0, that's my x-intercept. So 5/4 is just to the right of 1, and yeah, look at that. That confirms my expectation that this curve goes right here. And that's my only x-intercept, which confirms my expectation that this piece isn't going to cross this x-axis. I expect it to be down here. If I want to double check to ensure, I pick an x value on this side of my vertical asymptote. My vertical asymptote is at negative 2.5, so I'm going to pick negative 3 or negative 4. Let's just do negative 4. Let's do f of x equals, oh no, excuse me, f of negative 4. F of negative 4. So negative 4 times negative 4 plus 5 over 2 times negative 4 plus 5. Well, negative 4 times negative 4 is a positive 16. 2 times negative 4 is a negative 8. 16 plus 5 is 21. Negative 8 plus 5 is negative 3. That is going to be about negative 7, right? 21 divided by 3 is 7. Yep, that's going to be a negative 7. So where x is negative 4, y is negative 7. Yep, that works. That comes right in right there. So that is that function graph. Okay. I forget, you guys can pause your video. So I'm going to encourage you to pause the video right here and try to work out graphing h of x and f of x on your own. I'm going to graph them fairly quickly, talking through it just a little bit so that you can come back and look at it after you have tried it on your own. But I'm going to do it a little bit more quickly and quietly rather than taking lots of time to explain all of my steps. So pause the video, do these two graphs, and then pull the video back up. Okay. First thing, I want to do domain. I would check and see. I can tell kind of by looking, because I've got some experience, that that's not going to factor. That means that this is in lowest terms, and I don't need to worry about there being a hole in the graph. My domain value that I need to exclude is from the denominator, so all values x except 2. And because it's in lowest terms, I don't have a hole. That value 2 gives me a vertical asymptote, x equals 2. So I'm going to go ahead and sketch in that vertical asymptote. Symmetry, if I look at symmetry, since my vertical asymptote's over here, I do not expect to find any symmetry. If I plug in a negative x, that changes one term in my denominator, not the whole denominator. That causes me a problem right away. So symmetry, we're going to say, is not predictable. Horizontal versus slant asymptote, I compare the degree of the numerator to the degree of the denominator. And I see that my degree of the numerator is one greater than the degree of the denominator. So I know I have a slant asymptote, and I'm going to have to figure that out using my division. So I set up my division problem, x minus 2, 2x squared minus 5x plus 7. That gives me a 2x. And I get oh, that's not what I was, oh, no, that should be a 1. Sorry, guys, 1x, not 9x. So that is plus 1, negative 1, minus 1, negative x plus 2. When I subtract that, I get positive 5. Don't worry about that denominator. All I'm interested in is that quotient. So y equals 2x minus 1. Y equals 2x minus 1 is what I'm going to work with there. Okay. When I graph that, I start at negative 1, I go up 2 over 1, up 2 over 1, down 2 over 1. There is my slant asymptote. Then I look at y-intercept. Y-intercept happens where x equals 0. So if I plug in 0 for x into my function, I get negative 7 halves. Negative 7 halves is the same thing as negative 3 1/2. So where x is 0, y is negative 3 1/2. So that's going to be right down there. If y equals 0, I've got 2x squared minus 5x plus 7 over x minus 2. I multiply both sides by that denominator to cancel it out. That cancels and leaves me with 0 equals excuse me. Oh, that is factorable. I spoke too soon earlier. If I do 2x and x, oh no, it's not. Because those both need to be minus. I can't do a 7 and get a 5. That's not factorable. So I'm going to have some x-intercepts possibly. I would need to plug that into my quadratic formula to see if they are irrational or imaginary. So let's think about, no, this is not quadratic. This is quadratic. I can plug that into my quadratic formula. So x equals negative b is 5 plus or minus square root of b squared minus 4ac all over 2a. Right there, they're going to be imaginary because this ends up being 8 times 7. 8 times 7 is 56, and 25 minus 56 tells me that I'm not going to have any real x-intercepts. So let's think about that. If I don't have any x-intercepts, there are none. I've got to go through this point, so that means this piece of my function goes right there. And I'm not going to cross the x-axis. If I'm not going to cross the x-axis, I'm not going to be in these sides, which means the other piece of my function is going to be in that skinny piece right there. All right, last graph that we're going to do on this video. Let's do graph f of x equals x squared plus x minus 6 over x minus 3. That is factorable. Not in lowest terms. Yes, it is in lowest terms. Since it's in lowest terms, I have no holes in the graph. I need to exclude a positive 3 from my domain. And that gives me the location of my vertical asymptote. Because that has been shifted over, I'm not going to have predictable symmetry. If I plug in that negative x, it changes one term in my denominator, but not the whole thing, so I'm not going to worry about that. When I compare the degree of the numerator to the degree of the denominator, I see I have a slant asymptote. Now I'm going to take the quick way this time, and I'm going to use my synthetic division. Divide by positive 3, I've got 1, 1, negative 6. There's my equation for my slant asymptote, y equals x plus 4. Well, that y equals x plus 4 tells me that I cross the x-axis at positive 4 and I have a slope of positive 1. So my line looks like this. There's my slant asymptote. Pretend that's nice and straight. I apologize. Okay. Y-intercept where x is 0. Where x is 0, right here, x is 0, I get negative 6 over negative 3, which is a positive 2. 0, positive 2. That I see that I expect to have two nice x-intercepts, so let's set that equal to 0. X squared plus x minus 6 over x minus 3 multiplied by the denominator. 0 equals the numerator, x squared plus x minus 6, and we already saw that we can factor that into two factors, so those two values give me my x-intercepts. I've got negative 3, 0, and I've got 2, 0. At negative 3 and at 2, and look at that, there's my curve. Now what we have learned is that if we're in this skinny section down here, we're going to be in this skinny section up there. I can either do an additional point to check, or I can have confidence in what I have started to see going on with my rational functions. All right, let's switch over and do that final matching function page. It says to pay attention to asymptotes. We know that our vertical asymptotes come from the denominator, and our horizontal asymptotes come from comparing the degree of the numerator to the degree of the denominator. When I go through and look at these, I see that I have two slant asymptotes. F has a slant asymptote, and C has a slant asymptote. The others all have horizontal asymptotes instead. Well, how do I come up with a slant asymptote? I come up with a slant asymptote when the degree of the numerator is 1 greater than the degree of the denominator. So let's look down here and see what functions that I have fit that bill. As I compare the degrees of the numerator to the denominator, I see that 7 and 8 fit that requirement. The degree of the numerator is 1 more than the degree of the denominator. Okay, what's next? Well, I go back here and look and I see, you know what? This slant asymptote is positive on C, and on F, my slant asymptote is negative. Well, when I look at numbers 7 and 8, which one do you think, when I do the division, is going to have a positive slant asymptote? X squared divided by x is going to be positive. So that one is C. Negative x cubed divided by positive x squared is going to give me a negative value. So that graph, that equation, gives me the graph for F. Okay, so we got our slant asymptotes out of the way. How else can we narrow down these functions? As I look through, I see that I've got one vertical asymptote, two vertical asymptotes, one vertical asymptote, one vertical asymptote, two vertical asymptotes, one. Let's look at the ones with two vertical asymptotes next. Two vertical asymptotes. Functions, graphs B and G have two vertical asymptotes. B has a vertical asymptote at 0 and at 3, and G has a vertical asymptote at -3 and +3. My vertical asymptotes come from values that give me a 0 in my denominator. So I'm looking for equations for functions where I have a denominator that I can factor out. Which functions, 1 through 6, have denominators I can factor out? Well, that looks like numbers 5 and 6. If I factor number 5, my denominator, I can factor out that x and I get x minus 3. If I look at number 6, my denominator is difference of squares. So it factors out to give me conjugate pairs, and then I just have to match up these values to the correct vertical asymptotes. Number 5, if I set those equal to 0, I get 0 and 3, so that has to be graph B. Number 6, if I set those equal to 0, I get -3 and +3, so that goes with graph G, and we're halfway done. Okay, let's look at those remaining functions. Let's look at the equations for a minute. I see that for equation 1 and 4, I have vertical asymptotes at 0, because a 0 would cause me to have a value for 0 in my denominator where I'm undefined. So 1 and 4 are going to have to go with graphs H and E, because those are the graphs where I have vertical asymptotes at 0. The difference that I see immediately between H and E are that E has a horizontal asymptote at 0 and H has a horizontal asymptote at 1. Which one has a horizontal asymptote at 0 and which one has a horizontal asymptote at 1? Well, compare the degree of the numerator to the degree of the denominator. Less than gives me a horizontal asymptote at 0. Equal degrees gives me a horizontal asymptote at the ratio of the leading coefficients. 1 over 1 is just 1, so that one's going to be H. And now I only have 2 left. My last 2 to fill in have to be A and D. I see that equations 2 and 3 have to go with graphs A and D. And again, I already know where my vertical asymptote is. So now I need to figure out which one has the correct horizontal asymptote. Same rules. So I figure out that 2 has to go with D because my horizontal is at the x-axis. And A is going to go with equation number 3 because my horizontal asymptote is at a positive 1.